Hi everybody, I'm Razvi. Welcome back to the PWN101 series. In this video, we will be solving the 10th and last challenge from the PWN101 TryHackMe room. I've already downloaded the binary, and first let us see what kind of file it is. Once again, we will be facing a 64-bit executable that isn't stripped, which means that our life will be a little bit easier when reversing it. However, this time there is a small difference with the previous binaries we solved so far. In this case, the binary is statically linked. That means that the dynamic linker won't be required because functions are already present in the binary. They don't need to be resolved because their addresses are static. And we can check that by inspecting the size of the binary. As you can see, its size is huge. It's pretty big for just a simple binary. So now let us execute it and see what it's all about. Hello Pwner, I'm the last challenge. Well done. Now try to pwn me without libc. Given that the binary is statically linked, we cannot perform return to libc attacks because the dynamic linker won't be resolving any address. Functions are already present in the binary. In other words, the binary is standalone or self-contained, and whatever we may need in order to exploit it, we shall find it inside the very binary. So let us just input something random, and the binary just finishes. It doesn't even print some feedback to us. So now, without further ado, let's just reverse the binary and see what it's all about. I'll be using cutter just like every single previous video. And this time we can see that the function section is pretty big. Here you can see the scroll. That's pretty normal and is one of the consequences of the binary being statically linked. Let us take a look at the protections it has been compiled with. This binary has been compiled with canaries. There are canaries present on the stack with the no execute bit enabled. That means that we cannot execute shellcode from the stack, and it isn't a position independent executable. That means addresses won't change between executions. So let us take a look at the main function, and we can see it is pretty simple. It just calls to get, to printing some irrelevant information to the screen. Get is writing into memory from RBP-20 in hex, and it leaves, it returns. That's everything we got so far. So we know, of course, that get is a vulnerable function, which is vulnerable to buffer overflow attacks. And we should also notice that regardless of the binary being compiled with the canary protection, there isn't a canary check in the main function. That means that we can hijack the execution flow by overwriting the return address of main without being detected because there isn't a canary check. Okay, so how can we exploit this binary? How can we abuse it, given that it is very big? There are a lot of functions. We don't really know what to do with all of them. And we know that these addresses won't change. We cannot execute shellcode. And apparently, in the main function, there isn't a canary check. Now, I will show you the solution I implemented to exploit this binary and solve this challenge, but please be aware there isn't a single solution to this challenge. If you solve it in any other way, using any other technique, I encourage you to comment it down below in the comment section. Now, since this binary is pretty big and there is a lot of information and functions, I will go straight to the point, showing you how I solved it. The first thing I did is, of course, take a look at all the symbols and functions this binary exports, which, of course, took me a while. If you inspect all the functions, you will notice there is a function called make_stack_executable. Taking a look at this function reveals that there is also the mprotect function in the binary. Mprotect is a function used to change permissions of specific memory pages. So let us take a look at mprotect and see if we can leverage it somehow to exploit the binary. And we can see in the man pages it states that mprotect is used to set protection on a region of memory. As it is stated, mprotect changes the access protection for the calling process memory pages containing any part of the address range in the interval address length -1. Address must be aligned to a page boundary. This is very important, as we will later find out. Now we can also see that the protection parameter is a combination of the following access flags: protection none, read, write, and execute. As you may notice, these access protections are similar to those you can find in the file system, which is read, write, and execute. Let us see what is the value of each of these protections in the manH information. Here we have definitions for POSIX memory map interface, and here they are defined. The protection to read is 1, write is 2, and execute is 4. Prot is a combination of the following access flags: protection none, which means that the memory cannot be accessed at all, or bitwise, or of the other values in the following list. So in other words, if we want to change the access protections of any given memory region, making it readable, writable, and executable, we would have to perform bitwise OR of these values, and the resulting number is the protection that we want. So using a calculator, we can simply find out the value we want, and that is 1 for read, or 2 for write, or 4 for execution. And the result is 7. So 7 is the protection that we want to assign to a given address, memory address, if we somehow manage to call mprotect. Now, of course, bear in mind that if we were to call mprotect, we have to know what parameters this function takes. And we can see that we have address, length, and protection. So we need to know the address of the memory page whose protection we want to change. We need to know its length, how many bytes are we changing, and the protection we want, which is 7, as we have already seen. Before discussing about these two parameters, let us just remember that when we are exploiting a 64-bit executable, which is our case, in a Linux system, which is also our case, the parameters are passed via registers in the following order. Since we have 3 parameters, we are interested in changing these 3 registers right here: RDI, RSI, and RDX. Now that we are gathering a lot of information, I started writing down some notes. We know so far that gets writes at RBP-20, and we have the possibility to call mprotect, and in order to successfully call it, we need to modify the RDI, RSI, and RDX registers, corresponding of course to the parameters the function takes. We know so far that the protection is 7. And I have also declared the context and the variable we will use to interact with the process. And now just a bit of spam. Let me invite you to take a look at the last video I have uploaded, which will show you how you can debug your exploit and payloads whenever you need to do so. When we develop our exploit and we need to know how the script, the exploit, interacts with the vulnerable process and how the payloads are arranged into memory, you can do it by following this video, which is basically using the wait for debugger call from pwn110. Now let's go back to our binary and take a look at this function makeStackExecutable. You may think that we could just call and hijack the execution flow to this function. However, by doing so, we would have to care of all these operations the function is performing right before calling mprotect, which is our objective. So we can rather call it ourselves, crafting the parameters just as we need them. Now let's read a bit more about this mprotect function. One of the parameters it receives is len, which is the length of the memory it will try to change. As we can see here, the number we specify as len will be added to the address parameter, -1, and that's the whole page, the whole interval it will try to change. And here comes the trick. Here's when we find out what this sentence means. As you can see, it states that address must be aligned to a page boundary, that is, to the beginning of a memory page, because ideally we will change the whole memory page protection by specifying the beginning of the memory page and adding up the whole page size. So now the thing is, how can we know how long or how big a memory page is? Well, we can find out the page size of our local machine by using the getConf utility and specifying we want to know the page size. As you can see, it states that a page size is 4 kilobytes. This number is the number of bytes a page has. So we could basically assume that for our local exploitation, we can specify this size, and in the remote machine, they will be using the same. However, given that the makeStack executable function also calls mprotect, we can take a look at the page size it specifies when calling mprotect, so we can see what the binary intends to do with this function, which, by the way, isn't called. We can see the X references, the cross references for this function, and we can see nobody calls it. However, it is present in the binary for some reason. So if we take a look at this address right here, which is the specified page size, we will do so by using the hex dump view. We can see that it references an integer starting at this memory position. So remember that integers are little endian. That means that the least significant byte is written at the lower memory address. So in order to be able to make this number human readable, we can just invert the order of the bytes, which is also known as swap the endianness. That basically means that this is the most significant byte and this is the least significant byte. So let us just write it in that order. And that is hexadecimal for 00001000. As you can see, the number we have is 1000 in hexadecimal. Using the calculator in hexadecimal, we can find out that this number is nothing else than just 4 kilobytes. As you can see, this is its decimal representation. So by now we can just consider that our assumptions were correct, and this is the size of the page that we will specify to the mprotect call. So let us write it down, and now we have just one remaining parameter that we must somehow puzzle out. We have to determine what its value will be. And in order to do so, we have to go back and take a look at the symbols and function this binary is exporting. Upon closer inspection, I found out that there is a symbol called libc stack end. This object we have right here is of course an object that identifies the end of the stack. Of course, at this moment, performing static analysis, its value is of course 0 because it has no value, rather because this will be fulfilled when the binary is executed. This object, this symbol, is implementation specific. Nevertheless, in this case, we have it and we can abuse it. But how can we abuse it? We could basically print its value, leak its value, and use it to change the protections of the stack. That would in turn allow us to paste any given shellcode and execute it. So I have just noted the information. This is the address where this variable lives. And now how can we print the value of this variable during execution at runtime? Well, remember once again that this binary is statically linked. That means that we have everything we need inside of it already. So if we just take a look at the main function once again, we may notice it is making use of the put function. So there's nothing preventing us of also making use of this function to print information, to leak information to the standard output. This is the code of the puts function, which is present in the binary, so we can basically call it. As you can see, here it is, input output puts function. This is the address of the puts function that we will be using. Let us recap just for a moment. What we will be doing so far is abusing this buffer overflow to hijack the execution flow by overwriting the return address of main, and we will be redirecting the execution flow to the puts function in order to print the libc stack end variable we have just found out. This way, we will be able to discover where the stack lives during the execution at runtime. Now there's just one thing we didn't discuss about, and that is gadgets. Are there gadgets present in the binary for us to achieve what we want to do? Well, let's find out. I have used rob gadgets in order to find gadgets in the binary. As always, you can use the tool of your choice. Given that this is a statically linked binary, of course, there are tons of gadgets, but so far we are interested in, for example, the RDI register, because we want to print information to the standard output using puts function. And as you can see here, we have a match. This is the gadget that we need. So let me copy it since we will be using it. And now we have everything we need in order to write the first stage of the exploit. So far, in order to leak the address of the stack, here's everything we need. We need, of course, the pop RDI gadget, which is this address right here. We have just discovered with drop gadget. We need the address of the object libc stack end. I am using binary symbols from the elf module from pwn110. We need the address of main because we want to execute main once again after we leak the address of the stack. And of course, we need the address of puts. Then I am, of course, invoking the process. I am receiving until it finds libc, and then I perform just another receive, because remember that when we are executing the binary, here is the word libc, and then it has this garbage emoticon, so I want to get rid of it. Then the padding is, of course, 20 bytes to reach RBP. As we have previously discussed, gets writes from RBP minus 20. So I need 20 bytes to reach RBP, 8 more to overwrite RBP itself. And then I am placing the address of the pop RDI gadget, which will place in the RDI register the address of the libc stack end symbol. Then it will call puts, and puts will return to main, executing main once again. I am sending this payload I have just created and just spawning an interactive session because I want to see everything it prints. So let us find out. As we can see, here we have the value of the libc stack end symbol we are printing, and all this banner corresponds to the second execution of main. That is, our exploit was successful. We are executing main once again because we are printing the banner, and this is the value of the end of the stack. So we have to parse it somehow and see if we can get an aligned address in order to call mprotect. So first, let us parse this value. Now, in order to retrieve the stack end address that our exploit will leak, we need to, of course, receive all the output, split it by new line, and get just the first element of the list. Remember that there is a new line character after the address is leaked before printing the banner once again from the second execution of the main function. And the result of this operation will be left justified. That means padding to the right with zeros whenever is needed to make it 8 bytes long, 8 characters long. And of course, I am printing it, as you can see, unpacking it for 64 bits, because remember, this value will be big endian and I need its actual value, little endian, and converting it to hex because it's easier to understand. Let us execute once again the exploit. And as you can see, here we have the end address of the stack. Let me copy it. Now, please bear in mind that this address we have just leaked is the end of the stack at this particular moment of execution. We need to discover the beginning address of the page memory that contains this one, which is basically what is stated at this sentence. The address, the specified address, must be aligned to a page boundary. Now, we have previously seen that the page size is 1000 in hexadecimal. That means that somehow we must align this address to the 1000. In other words, we want to obtain this particular address. This is the beginning of the page. So how can we just align every single address we are leaking? We can achieve it, of course. We can get to this number by putting to 0, transforming into 0 the least 3 significant bytes of any given address. We can do so by using the bitwise operator AND with the page size -1, which is FFF, and by negating this value. Negating this value will result into every single bit turned on except those corresponding to the least 3 significant bytes. And by performing this operation, we will obtain an aligned address regardless of the value we are working with, which is basically what this sentence states, which in Python is just as simple as that, performing AND operation and negating this value right here. And just let us test it. As you can see, regardless of the value I am leaking, I am obtaining, of course, the aligned address. And this is the value of the address we want to pass to mprotect. Now, in order to call mprotect with the parameters we have just discovered, we need, of course, the corresponding gadgets to do so. Let's see if there are gadgets to modify RSI and RDX in the binary, which there happens to be. We have the needed gadgets in order to perform the mprotect call. And let us think a bit for a moment. After we change the protections of the stack, what do we need to do? We could basically execute any given shellcode. I will be using this one right here from exploit database. You can use any shellcode that works for Linux 64 bits. And we are placing the shellcode in the stack, but somehow we still need to execute it. We need to redirect the RIP instruction pointer register to this shellcode to be able to execute it. And in order to do so, given that there are gadgets galore in this binary, one of those gadgets is jump RSP, which will allow us to jump to wherever RSP is pointing. I have translated into actual addresses, the addresses of the gadgets we need, also the jump RSP gadget, and we also need the address of the mprotect function. Then, after the first stage of our exploit, when we are leaking the address of the stack end object, and we basically calculate the page aligned address, in the second stage, we are defining the shellcode that I have obtained from exploit.db, and we are creating our new payload using the padding, of course, and then using the RDA gadget to place into the register the stack aligned address, which corresponds to the page boundary align address parameter of the mprotect function. We need the page size, which we have seen is 1000 in hexadecimal, and the protection we want, which is 7, that corresponds to readable, writable, and executable. Then we need to call the mprotect function, and here's the trick. When the mprotect function will execute its return instruction, the RSP register will be pointing right to the address of the jump RSP. After the return instruction is executed, the RSP register will be moved, incremented, one address pointing to the shellcode. And then the RIP register instruction pointer will execute the jump RSP instruction, jumping right to our shellcode. Just a quick sketch to better visualize what is happening here. Imagine we are just about to execute the return instruction of the mprotect function. So the RSP register, the stack pointer, will be pointing to the address of the jump RSP instruction that we have placed in the stack, and right above it is our shellcode. So we will now execute the read instruction of the mprotect. The first thing that will happen is that the RSP register will be incremented, pointing it to the shellcode, and the instruction jump RSP will get executed because the RIP, the instruction pointer, just moved there. And when the jump RSP instruction is executed, the RIP instruction, the instruction pointer, will be basically assigned the same value as the RSP register, which in turn points to the shellcode, thus executing our shellcode. So let us now test it. As we can see, we are successfully executing our shellcode and spawning a shell locally. Let us now test it remotely. However, if you have a hard time understanding why this payload works, or you feel like you don't fully understand how return-oriented programming works, I recommend you watching a video you can find in this channel called Exploiting Return-Oriented Programming Tutorial, in which we dig deep into what the read instruction does and which are its effects regarding the RSP and RIP register. Now I have transformed the exploit to work remotely instead of a local process we want to connect to a given IP and the port, and I have also placed an extra read instruction, which I have previously found as a gadget, which is simply a read instruction, because remember that remotely we are working with a Ubuntu 18 machine, which usually gives stack issues, alignment issues, that we can solve by placing an extra read, of course, after the padding. So now let us execute the exploit. Here we have it, and apparently we have managed to successfully get a shell. Now we can just print our flag. which let me check whether it is correct. And apparently it is. In this video, we have seen how we can successfully abuse a simple buffer overflow to exploit a binary that was statically linked. By making use of functions already present in the binary, like mprotect and puts, we were able to successfully leak addresses from the stack and make the stack executable, thus bypassing the no execute bit which the binary has been compiled with. In other words, we managed to successfully execute shellcode when we weren't allowed to in the first place. I hope you liked the video and found it useful. If there's anything you want to say, leave a comment below, and remember, exploit code, not people. See you in the next one. Until then, GG.